In the last lesson, we learned how to calculate the heat that's involved in state changes. So when a solid becomes a liquid, when a liquid becomes a solid, or when a liquid becomes a gas or a gas becomes a liquid. We were looking at these plateau areas here. Okay? Now what we're going to be focusing on is when the temperature of a substance changes, how much heat is involved in those processes. So this right here, what I just highlighted, is the range where a solid changes temperature. This is where a liquid changes temperature, and this is where a gas changes temperature. So we are concerned with how much heat is required to increase the temperature of a solid, a liquid, and a gas. And that's what we're going to be considering here. So there is a formula for determining that heat, and here's the formula. It is Q equals mc delta T. Well, we often call it MCAT. Okay? So let's talk about what each of these variables represents. Q is your heat. Okay? So the amount of energy transferred that is required for the temperature of a substance to change. And the units for that are joules. M, as you probably suspected, is mass. And the units for that are grams. The new unit that we haven't discussed yet is your specific heat capacity. Okay? And your specific heat, its units are going to be joules per gram degree Celsius. And I'll explain that in just 1 second. I need to go over the last variable, and that is your change in temperature. Okay? And specifically, it is your final temperature minus your initial temperature. Okay, TF, TI. Final minus initial. Okay, and the units for that are going to be in degrees Celsius. Okay, so why are the units for specific heat joules per gram degree Celsius? Well, if you think about it, since my units for heat are joules, okay, what I'm multiplying here is mass, which is grams. So the grams cancel because these grams are on bottom, these are up top, and degrees Celsius on bottom, which cancels with this temperature. So what I'm left with is just joules, which is the units for heat. Okay? So let's look at these calculations. Just as a quick reminder before we do that, remember when we were looking at state changes, if I was moving from right to left, then the sign of the heat would be negative because heat is being released. If I was going from a liquid to a solid here, freezing, my heat would be a negative value. So when I was moving backwards, the heat that I calculated was always negative. When I was going forwards, it was always positive. Same thing here. If I'm going from here to here, I'm decreasing in temperature. So the heat value that I calculate should be negative. If I'm moving from here to here, my temperature is increasing, so my heat value should be positive. So let's look at that play out in these examples. So example 1 says, calculate how much heat in joules must be added to 50 grams of water to raise its temperature from 17 to 37 degrees Celsius. And it tells me my specific heat of water is 4.18. So I'm going to be using my formula, Q equals mc delta T. Okay. I know my mass is 50 grams. I'm told my specific heat is 4.18. Now here's the calculation that I have to do. Remember, your change in temperature is your final temperature minus your initial temperature. So my final temperature is 37 degrees minus 17 degrees. So my change in temperature is going to be 20 degrees Celsius. Now, keep in mind, this has no decimal places. This has no decimal places. So when I plug in the 20, I don't want to just put 20 because that would be just one sig fig. I want it simply noted that it has no decimal places. So I'm going to put a decimal here so that this will have two significant figures. This value makes sense quickly for you to be able to check yourself. If I'm going from 17 to 37 degrees Celsius, my change in temperature should be positive. It should be positive 20 degrees. Okay, and it is. So 20 degrees here. Okay, and now all I have to do is calculate. So 50 times 4.18 times 20, and I get 4,180. Okay, keep in mind, I've got to figure out my significant figures. So 50 has 1, 2, 3, 4.18 has 3, and 20 has 2. So this is going to round to 4,200. And remember, my units for heat are joules. Okay, let's look at the next problem. It says a 590 gram brass candlestick has an initial temperature of 98 degrees Celsius. If 21,100 joules of heat is removed, that's important, we'll look at that in a second, to lower its temperature to 6.8 degrees Celsius, what is the specific heat of brass? So now instead of asking you to solve for heat, now I'm asking you to solve for the specific heat, or your C. Okay, so let's write out my formula again. Q equals MC delta T. Okay, keep in mind, it says 21,100 joules of heat is removed. So if it is losing that amount of heat, then the value that I put in for my Q, instead of being positive, it needs to be negative. Okay. I know the mass of my candlestick is 590 grams. It's asking me to solve for my specific heat, so that's my C. Okay. And then I need to plug in my delta T. So remember, delta T is final temperature minus initial temperature. Okay, so my final temperature in this case, it says it went from 98 degrees to a temperature of 6.8 degrees. So 6.8 is my final temperature. My initial temperature is 98.0 degrees Celsius. Okay, so when I subtract 6.8 minus 98, I get negative 91.2. Keep in mind, when you're subtracting, you want to round based on decimal places. I've got 1 decimal place here, 1 here, so that works perfectly. So negative 91.2. Now, I simply need to solve for my C. So I will first multiply 590 by negative 91.2. And what I get here is negative 53,808 times my C. Okay, equals negative 21,100. Okay, and then I'm going to divide both sides by the negative 53,808. And what I get for my specific heat, my C is going to be 0.392 13. Okay, keep in mind 590 has 1, 2 sig figs, negative 91.2 has 1, 2, 3 sig figs, and then my heat has 1, 2, 3 sig figs. So my final answer needs to have 2 sig figs, 1, 2. So my specific heat is 0.39. Okay. Keep in mind, to get my specific heat, I divided joules, my heat in joules, by the mass in grams, and by the temperature in degrees Celsius. So those are the units for my specific heat, joules per gram degrees Celsius. A really easy way to check yourself, if you forgot to put the negative for your heat, you would get a negative specific heat, and the specific heat for a substance will never be a negative value. Okay? The specific heat for every substance is unique, just like density is. So when we're talking about the specific heat of a substance, it's going to be different whether it's water, as you can see here, 4.18, versus metals, which have a much lower specific heat, like brass, 0.39. Okay? Let's look at another example. A chemistry student finds a shiny rock that she suspects is gold. She weighs the rock on a balance and obtains the mass, 14.3 grams. She then finds the temperature of the rock rises from 25 to 52 upon absorption of 174 joules of heat. Find the heat capacity of the rock and determine whether the value is consistent with the heat capacity of gold. So this is similar to the previous problem we just did, Q equals MC delta T. And I'm going to be solving for the heat capacity or the specific heat. Those terms for us will be interchangeable. So I know that it absorbs 174 joules of heat. I know that the mass of it is 14.3 grams. I'm solving for my specific heat or my heat capacity, and I want to find my change in temperature. Remember, change in temperature is final minus initial temperatures. Okay. I know my final temperature here is 52. I know my initial is 25. So the change in temperature is going to be 27 degrees Celsius. So I can plug that in here. Now I'm going to multiply 27 by 14.3. So what I get, 174 equals 386.1 times my specific heat. And then I'm going to divide both sides by 386.1. And so the specific heat that I get is I want 2 sig figs, so this would round to 0.45. And my units again are joules per gram degree Celsius. Okay? It says, determine whether the value is consistent with the heat capacity of gold. So the heat capacity of gold is 0.128. This is the heat capacity that I calculated, so it is not consistent. So this is one of the values of your specific heat. You can determine the identity of a substance or rule out the identity of a substance by measuring the change in temperature, knowing how much heat is involved. You can therefore determine the heat capacity and compare it with known values to figure out what the substance is. So here, I know that this substance is not gold because its specific heat does not match up with that of gold. For the last problem, a 328 gram sample of water absorbs that much heat. Calculate the change in temperature for water if this is the heat capacity or the specific heat. Okay, so Q equals MC delta T. I know that the heat involved is 5.78 times 10 to the third. Okay. I know the mass of the substance is 328 grams. I know that the specific heat of water is 4.18. Okay, and I'm solving for my change in temperature now. Okay, so 328 times 4.18 gives me 1,371.04 times my change in temperature. That equals my heat, 5.78 times 10 to the third. I'm going to divide both sides by 1,371.04. And the change in temperature that I get, what I get unrounded is 4.2158. Notice all my values have 3 sig figs, so 1, 2, 3 sig figs. So my change in temperature is 4.22 degrees Celsius. So this is my change in temperature. It increased by 4.22 degrees Celsius. The question goes on to say, if the water is initially at 25, what is its final temperature? Well, if it started at 25 and it increased by 4.22, then I need to add that 4.22 to find the final temperature. Okay? So this would be 29.22. Keep in mind, since I'm adding, my final rounding will be based on decimal places. So since 25.0 has 1 decimal place, this will just be 29.2 degrees Celsius. Okay? If the value had been negative, if my change in temperature had been negative, then it would be 25.0 plus negative 4.22, and then the final temperature would have been lower, which is fine as well.